In section 7.6, we learn of a way to handle what I would call backwards conditional probability, and that's called Bayes' theorem. Backwards conditional, I'll have to explain that in just a minute, but it'll make more sense as we talk about it. And you have the formula in your textbook, and so your textbook shows you very nice ways to work with the formula. It can be a little messy, but it's nothing that I think you can't handle. Certainly, you can use a formula. What I'm going to show you is kind of what my job is, which is explaining other ways to approach things other than just the textbook method. So the textbook uses the formula. So what I'll do is I'll show you how you can use a tree diagram, which really simplifies things very nicely. But of course, I'm open to you using either method. So I think jumping into a problem will help us understand what I mean by this idea of backwards conditional. Notice that was in quotes. That's not a technical term. It's an idea. And how we would approach these. How are they different from what we've talked about before? So let's just take a look at the example. So we're told a certain virus infects 1 in every 200 people. We develop a test for this, and the test detects a virus in a person 80% of the time if the person has the virus. So some people would call that 80% accurate, even though there's not a real meaning to the term 80% accurate that is common to everything. And then it says 5% of the time if the person does not. So it actually says positive 5% of the time, even if the person doesn't have the virus. And you may say that's bad, but there's no such thing as a perfect test. So the question is, you test positive for this. Somebody tests positive for the virus. What's the probability they actually have the virus? Some people would automatically jump and say 80%. But remember, that's a conditional probability. It's saying if the person has the virus, the probability of testing positive is 80%. We're actually asking the reverse. So this is what I mean by backwards. We're saying, what's the probability of the virus? I'll use that for infected, given we have a positive result. So in other words, we know the result. When the person walked into the doctor's office, they either had the virus or they didn't. And so we know the end result. That's backwards. That's out of order. We want to know, did they come in originally with the virus or not? So that's what I mean by backwards conditional. So the tree diagram approach to this, and this works actually for any problems, including those in 7.4 and 7.5. Tree diagrams are great to understand probability. But anyway, for this particular problem, we say, okay, what was the first thing that happened? Well, the person had the virus or they had no virus, right? That's the intermediate step. Then they take the test. Either they had the virus and then they could test positive or negative because it's not perfect, or they did not have the virus and they could test positive or negative. Now I start filling in probability. So the question is, what's the probability the person has the virus? Well, based on our data, it says 1 out of every 200 people. So this would be 1 out of 200. That means the probability of no virus would have to be 199 out of 200. In other words, it'd be 1 minus this probability. Okay, now the test is used, and it says again, used in a person is positive, or detected virus in a person positive 80%. So I'm scanning this if the person has virus. Okay, so if the person has a virus, positive 80% of the time. That means it incorrectly says negative 20% of the time. That's important. All right, and it says 5% of the time the person does not. So it's going to say positive 5% of the time, even if the person doesn't have the virus. So no virus, 5% chance you'll be given a positive, 95% chance you'll be given a negative. All right, so Bayes' theorem, Bayes' formula, however you want to state it, what it takes into account is the big picture and small picture, just like we're used to. So what's the big picture? Well, we know the person tested positive, right? So either they had the virus and tested positive. Remember, multiplication to find and probabilities, or means add. They did not have the virus and they tested positive. So the big picture here would be virus and positive, so 1 out of 200 times 0.8, or no virus times probability of being positive, 0.05. So no virus and positive. Okay, now what picture are we interested in? We're interested in the probability the person has the virus, given they tested positive. And so we're looking at virus and positive as the small picture, and so that would be the top. Again, that's the general idea of every probability question we've ever done. Small picture over big picture. It's always changed. The only thing we've ever changed is how we approach the idea of what is the big picture, because sometimes it's more complex. So that's really what Bayes' formula or Bayes' theorem is. And so you have to calculate this. Now, for this one, I would highly recommend practicing on your calculator, because it's very common for students to get this the formula right and then manage to get the overall numbers wrong. So make sure that you're using parentheses on your calculator liberally and that you get the same result as me. Double check your answers. So when I calculate this, I actually get 0.0744. So I want you to think about that for a minute. It's saying if you test positive, the probability that you actually have the virus is only 7%. So I think that that's a very interesting problem. Like, why is that true? Why is this number so small? And so one time I said that in class, and a student said, because you made it up. And okay, fair enough. A lot of these problems are made up data, right? However, this is a common type of probability that doctors would calculate, and they get also similarly strange results. First of all, it shows that our intuition about probability is off. And second, and that's for everybody. And second, it shows that when a virus is pretty rare, 1 out of 200 people, okay, that's more common than you might like, but it's not that common. The more rare this is, the lower the probability already that somebody's carrying it is. So imagine if this is 1 out of every 200, 2,000, 20,000, right? Something even crazier. And then this right here is pretty low. Even when this is 95%, you actually get some interesting values, but this is pretty low. So again, this test is accurate, highly accurate, but not astoundingly accurate. It's still 5% of the time gives positives to people without the virus. What's the most likely thing that could happen? You have no virus. And so again, that's heavily weighing on this, and how often it gives a positive correctly versus not is weighing on this as well. So Bayes' theorem is a very interesting tool, and it shows us again how difficult it is sometimes to wrap our minds around conditional probability. So you'll find that you'll get really strange results, or at least they'll seem strange to you when you're working on these, and you should be confident that you did it correctly. So this is something interesting. If you find this interesting, there's lots of articles out there worth Googling as far as applications of this and results that you end up getting. But for us, we say, okay, that's the method. We're learning how to approach these problems, and so we'll do one more to kind of see how it all works out. So in this case, we're told a distributor has 100 boxes of radios. Okay. Factory A ships some of them, Factory B ships some, and Factory C ships some. All right. The probability of a radio being defective is 0.04 if it came from A, 0.02 from B. So this is saying that some of the boxes are messed up at different factories, and they have different rates of how often that occurs. Finally, we say, okay, a box and a radio from that box are both selected at random. The radio is found to be defective. Find the probability it came from Factory B. All right, so when we talk about a box being selected, we're assuming that that whole idea of the radio and the box being selected are kind of the same thing for us. And let's write down what this probability is asking. This is saying probability came from B, and remember, the radio is found to be defective, so given defective. This is also backwards because, remember, it was either defective or not. It came from B or A or C first, and then we determined if it was defective. But we're looking at it in the reverse. We're saying, okay, we know the end result. We know it's defective. Where did it come from? So if you think about the life of one of these radios, they either start from A, B, or C, right? And then they're either defective or not. All right, now I start filling in the probability. So when they come from A, that would be, or what's the probability they come from A? 35 out of 100, so 0.35. From B, 40 out of 100, so 0.40. And from C, 25 out of 100, or 0.25. All right, and then we're told 4% from A are defective, 2% from B are defective historically, and 6% from C. So already think about it for a second. Most likely it came from B. However, most of the defective ones come from C. So these kind of probabilities are almost battling it out in our formula. All right, now I'm going to fill in the other side of it. This would be 96, this would be 98, and this would be 94. All right, so same idea, big picture, small picture. So the big picture is we know it's defective. How many different places could it have come from? We don't know. So it could have come from A and B defective, so that'd be 0.35 times 0.04. Or it could have come from B and B defective, so 0.4 times 0.02. Or it could have come from C and B defective, 0.25 times 0.06. Now the small picture is we want to know the probability that it came from B and was defective, and so that's what goes on top. So that would be 0.4 times 0.02. Okay, so once again, I highly recommend that you calculate this on your own and make sure you get the same value as me. And when you do that, you should end up with 2162. So even though 40% came from B, if we know it's defective, there's only a 21% chance it actually did come from B. And again, that's because not too often are those coming from B defective.